Hello. In this lecture, we will be discussing how to use recursion trees for analyzing divide and conquer algorithms, or how to find time complexities of divide and conquer algorithms. In divide and conquer algorithms, a problem of size n is divided into a subproblems of size n by b of same kind, where the problems are of the same kind. So we will write recursive algorithms for those problems. So now we have a such subproblems and each of size n by b, so we'll get a recurrence relation as T of n is a into T of n by b plus f of n. F of n is the time for dividing and merging. Okay, so let us try a recursive tree or a recursion tree for this. So we start with a problem of size n, and in the first level it will be divided into a subproblems of size n by b. So there are a subproblems. So there are a function calls, each of size n by b. And in the second level we have a square subproblems or a square function calls, each of size n by b square. At ith level we will be having a power I function calls and each of size n by b power I. Now, what is the depth of this recursion tree? So to know the depth of the recursion tree, as we know at each step it is reduced by b, that is n by b, or it is divided by b. So now let us suppose after k steps it is reaching to a base case. So then n by b power d is equal to, or n by b power k equal to 1. So from there we can derive that k as log n base b. So the depth is log n base b, and the number of leaves. So at depth log n base b, we will be having a power log n base b number of leaves, and a power log n base b we can write it as n power log a base b. So now to analyze, so the work done, or the non-recursive work done at problem of size n is f of n, and in the first level each node the work done is f of n by b. A such nodes are there, we will get a into f of n by b. And in the second level we have at each node f of n by b square, and there are a square number of nodes are there, so that is a square into n by b square, the total work done at level 2. So on, if there are L levels, then we have a power L into f of n by b power L. That is the total cost. So when you sum it up, you are going to get something like the total cost by considering the sum of work at each level, that is f of n plus a into t of n by b plus a square into f of n by b square, so on, a power L minus 1 into f of n by b power L minus 1 plus a power L into t of 1, and t of n is the work that is at a leaf level. It is if you consider t of 1 as order of 1, then we are going to get a power L. As we know that the number of levels is log n base b, so we get a power log n base b, so it is equivalent to n power log a base b. So the work contributed by the leaves is big O of n power log a base b. Now for simplification, we will consider f of n as big O of n power k. It will cover most of the cases in our course. That's why we are considering f of n as big O of n power k. Okay, that means f of n is some polynomial in n. When f of n is big O of n power k, depending on the values of a, b and k, how one can decide what is the time complexity of those algorithms. That's what we will be discussing now. So first, suppose a is b power k. A is equal to b power k. When a is b power k, that means the number of subproblems that we are going to consider is equal to b power k. Now, as we know, suppose we consider at a depth I, the number of nodes at level I is a power I, and each problem of size n by b power I, and work done at each level is f of n by b power I. That is, if you substitute in n power k, so then you will get some constant into n by b power I whole power k. Now the total work at level I is, because ai subproblems and each requires f of n by bi, so we'll if you multiply these, then if you take out this n power k common, then we'll get c into n power k a by b power k whole power I. If we assume that a is equal to b power k, or if we consider a case where a is equal to b power k, then it is 1, then we will get the total work at a level I as big O of n power k. Okay, so how many such levels are there? Log n base b levels are there, and in each level we require n power k. So the time complexity is big O of n power k into log n base b. Okay, and as we know, at the leaves we require big O of n log a base b, and as it is the lower order term n, and if you substitute a as b power k, so we'll get big O of n power k. So the total time complexity is big O of n power k log n. This is, when a is equal to b power k, we can say it as big O of n power k log n. Now we will consider the second case when a is b power k. That means the number of subproblems are growing faster. When the number of subproblems are growing faster, the work done at the leaves dominates the work done at the root, or the number of leaves grows faster. So now with a similar argument, with the number of subproblems is at a level I is a power I, and the number of subproblems is a power I, and each problem of size n by b power I. If you want to multiply the total work at I, that is, with a similar argument, we will get c into n power k into a by b power k, and if you take n power k common, so we will get this. And as a is greater than b power k, and this ratio is greater than 1, when you have such a series, when it is added, it is dominated by the last term. That means at the last level, when you have at the leaves, so you have that at the leaf level, that is log n base b. The level is log n base b, so we have c into n power k a by b power k log n base b. This, by using identities of the logarithm, we can write it as c n power k n log a by b power k sp, so it is in the form of log a by b, so we can write it as log a minus log b, so we'll get, and we have log b power k, so we will get k. So n power log a base b minus k, and n power k is there, so when you cancel it, so you will get c power n log a base b. So the total cost of the time complexity is big O of n log a base b. When when a is greater than b power k, we can directly say it as big O of n log a base b. Now we have a third case when it is a less than b power k. The number of subproblems grows slower than the b power k term. So in that case, with a similar argument, we can say that the work done at each level is c into n power k a by b power k. When a is less than b, the sum is such a series is dominated by the first term, that is the work at a root. The work at a root when it is I is equal to 0. So when I is equal to 0, then you will get c n power k a by b power k 0. So we will have a big O of n power k. Now the time complexity is T of n is big O of n power k. So let us summarize these three cases. When the recurrence is in the form of T of n is equal to a into Tn by b plus big O of n power k. When a is equal to k, we can directly say the time complexity as big O of n power k log n. When a is greater than b power k, we can say it as big O of n power log a base b. When a is less than b power k, we can say big O of n power k. And in each cases, in the first case, the work is balanced across all the levels, and work increased towards the leaves in the second case, and work is decreased towards the leaves. So this recursion tree provides an intuitive foundation to the Master's theorem. The same arguments that we will be giving in the Master's theorem also. That Master's theorem we will be discussing in the next lecture. So now these are the homework problems. So by using the above three cases, find the time complexities and give arguments. And this is, so let us summarize what we had discussed in the recursion trees. We started with the definition of a recursion tree and how we can use to visualize the flow of execution and how to find the time complexities. This can also helpful in finding overlapping subproblems and finding redundancies so that we can optimize it. That is something that we will see in the dynamic programming case. Thank you.